Hello everyone, and welcome back to a Chemistry 241 lecture. We're starting chapter 12 today, and on today's schedule we're supposed to be going through sections 1 through 4 of chapter 12. Now chapter 12 is kind of interesting because it says synthesis, all right, synthesis. And basically at the core of organic chemistry is making stuff, all right? Making drugs, making pharmaceuticals, making perfumes, paints, pigments, you name it. And the chapter 12 here takes you through a lot of different synthetic strategies. And as I have been trying to stress over the past few lectures, you need to make flashcards or lists or however you use to memorize reactions and go through those frequently and often. And we don't want to be struggling to try to find one particular reaction for a one-step synthesis. Section 12.1 says just that, one-step synthesis. Okay, and these are synthetic transformations that require only one step. Now keep in mind, a one-step synthesis could still be something like this, right? Where you have hydroboration, then oxidation. So I call this a one-step synthesis, all right? And the book does as well, okay? And the book says, and I quote, I'll just quote the first sentence here of the section, "The most straightforward synthesis problems are the ones that can be solved in just one step," okay? And let's take a picture here of 12.1 and just do these to get all warmed up. Okay, I'll do this here. Kind of got a glare here, but let's try that. Okay. And these are alkenes, right? There's an alkene in the middle there. And let me trim this up a little bit. They say these reactions come from chapter 9. Okay, so here we go. So let's see here. The problem says identify the reagents necessary to accomplish each of the transformations shown below. If you are having trouble, the reagents for these transformations appear in the review of reactions at the end of chapter 9. But you should first try to identify the reagents yourself without help, all right? And so here, it's basically just memorization. There's no thinking or anything. You just need to memorize these things. So do not worry about this reaction. Let me identify all the other ones that we haven't talked. Okay, so we're good. So here we add HBr, that's Markovnikov rule. Here we can do ozonolysis, zinc and acid. Here, these two groups are on the same side. So we want to do a syn dihydroxylation. Cold potassium permanganate works well for that. Here we have an anti-dihydroxylation. So we can use MCPBA, okay, and then acidic workup. Here we've got a bromohydrin, so this would be bromine and water. Okay. Here we have vicinal dibromide, anti, right? Bromine does that. Here we're erasing the double bond. That would be hydrogen with maybe platinum as a catalyst. And here it's hard to see, so what you need to do is add in the group here. There's an H that's been added. Now you can see that it's a syn, okay? And that's a hydroboration that let's see if I could squeeze this in, BHF, THF, and then basic hydrogen peroxide. So NaOH is your base. Here we're just hydrating, so water with an acid catalyst. Here we're adding HBr. And we skipped chapter 11. We'll come back to that. So don't worry about this reaction, okay? All right, so that's warming up. That's section 12.1. Let's do problem 2. Problem 2. I've tried to do these before in the classroom when we could meet in person, and it ends up taking the whole class period. And it's a good kind of reminder for students, well, hey, if you don't know these reactions really quickly, you're going to have trouble with something that comes later on in this chapter. So it's a good wake-up call for students usually. Here I'm just doing it for you, and it's it can be misleading. It can seem as easy as me doing it or as easy as watching a video. All right, so here we have alkynes, okay? Let me read the problem to you so you can get oriented. Identify the reagents necessary to accomplish each of the following transformations. If you are having trouble, the reagents for these transformations appear in the review of reactions at the end of chapter 10. But you should first try to identify the reagents yourself without help, okay? So what do? We don't worry too much about this mono guy, but if we treat this with HBr, right, we say excess or 2 equivalents, we can go straight to that guy there. Excess or 2 equivalents NaNH2 can make the alkyne, okay? 2 equivalents or excess of NaNH2 can make the alkyne. Ozonolysis cleaves triple bonds, okay? These would make great reactions for your flashcards, so, you know, each one individually. Don't put the whole thing on one flashcard. Here we're adding water, 2 hydrogens, 1 oxygen, and the richer get rich, so this is going to be a hydration. You might think water and acid, but you've got to do that weird thing with the mercury there. Okay, so mercury ion, water, and acid. This is the anti-Markovnikov addition, so we're adding 2 hydrogens on the left carbon. So that's your hydroboration procedure. And number 2 is your basic hydrogen peroxide. Now this is like all of the homework that we just did. You're going to add sodium amide and then some alkyl group. Here we just want 1 carbon. So that's CH3, and choose a leaving group. We can add 2 equivalents of bromine to give the tetrabrominated guy there. And then various hydrogenations can be used to transform alkynes to alkenes. So, okay, so that's warm up, all right? These should all be on your flashcard. Chapter 9 and 10 were already discussed, and these are things you should be going through every day. Just spend 5 minutes, boom, boom, boom. If you do that 2 or 3 hours, every 2 or 3 hours in a day, that would be even better, okay? If you're trying to memorize something, it's a little bit more efficient if you spend less time, more times a day to try to drill it in, okay? Again, that takes tremendous amounts of self-discipline, but if you can manage that, that would be the best way to memorize these various reactions of alkenes and alkynes. Now, the book gets into pretty much what we've already talked about before. 12.2 talks about functional group transformations. Okay, so as a review here, let's just talk about the different functional groups we've talked about. We've talked about alkyl halides, We've talked about alkenes. We've talked about alkynes. And we've talked about alcohols. Now, there are different synthetic strategies that enable us to move from one functional group to a different one. And so sometimes you want to change something like this to something like this. Okay. Now you can't do this in one step. You first have to change this to an alkene and change that alkene to a different alkyl halide. So we can add HBr to alkenes, and we can do an elimination. Now when you do the elimination, remember the different types that you're going to be doing. Here we have to use sodium ethoxide to get the Zaitsev rule. Okay. So keep that in mind, as I mentioned in the alkene chapter. The alkenes are the link here. Okay. Now, if we have alcohols, perhaps it's better if I just maybe take a picture. There's a lot of writing here. This is a scheme in the textbook. Okay. And this is, a good scheme to talk about here for a moment or so. Look what we're doing. We're taking an alcohol and making an alcohol, but it's in a different location. Now, there's different ways of doing this. Okay, different ways of doing this. We know that alcohols can be dehydrated by treating this with acid and heat like we did in the lab. Okay, so if we add H plus and heat, we can get the alkene. And then if you add water and acid, I write H2O and then H plus, so we can see the different components. You can form the alcohol through the Markovnikov addition. Okay, and so that's all fine and dandy there. Now, to do this bottom reaction, okay, where you change the alcohol at carbon 2 there to an alcohol that has the hydroxyl group at carbon 1, okay, we need to do something different. We need the carbon-carbon double bond to be between carbons 1 and 2, and somehow we have to get the OH on the less substituted side. So we do that through the anti-Markovnikov addition, but to get to the alkene, we have to use toluene, sulfonyl chloride, and pyridine, and then treat that with a potassium butoxide. So let's make a note of that on the next page. Everything here is, we've talked about it and we've seen it before. But I just want to mention that if you have an alcohol, okay, and we need this to be a good leaving group, we can treat this with toluene sulfonyl chloride and pyridine. We just write PYR, okay, and that makes the tosylate, okay. So that guy right there is called the tosylate, and that's a good leaving group. And so if we treat that with a base, for example, we will get the alkene, for example, okay? How does this work? Well, in case you're wondering how this works, the alcohol here is a nucleophile, and toluene sulfonyl chloride looks like this, okay? And I don't want to get into this too much, but this molecule here can undergo an SN2 reaction, kick off this sulfur here, kick off the chlorine, I mean. Okay, and what you get, so that's the attack step. What you get after that, so this molecule right here that I drew out is TSCl. You don't need to ever remember the mechanism for this, but I'm just writing it out so that maybe this will reinforce some things that we've already learned. So you have a molecule that looks like this now, okay? And we can deprotonate this with a molecule called pyridine. Pyridine is an aromatic amine. Various uses of this molecule. And so this is a base, and it can deprotonate this guy here to give you this molecule right here. So the OTS is an abbreviation for this whole part of the molecule. Okay. So that's a tosylate. So the alcohols can be converted to tosylates, and that's a good leaving group, okay? So that's a new reaction that you should learn here in this chapter, okay? Moving on, we can see that there's this feature here where you can change triple bonds to double bonds to single bonds. And this is again is a functional group transformation. And I just want to highlight all of the relevant reactions here. Okay, so a very common strategy might be to form an alkene from an alkyne. You can do that in one of two ways. So remember that Lindlar's gives you the cis and sodium gives you the trans. Okay. To transform an alkene to an alkyne, you've got to do 3 steps there, okay? So say, for example, we have this molecule here. And I want to treat it with 1, 2, 3. So let me go through what happens. Bromine is the reagent. Okay. CCl4 is just a solvent. Okay, it's a typical halogenated solvent. Anyway, so this forms the dibromo. Okay. And as I mentioned before, what I do, I'm quite lazy with this. I just write 2 equivalents of NaNH2. Okay. And so 2 equivalents of NaNH2 gives you the alkyne. Okay. And so, yeah, that's a very, very common type of thing. This is chapter 11. We'll talk about that later. Okay, but we do know how to hydrogenate. We might even add this reaction here too. H2 platinum can change the triple bond to a single bond as well. Okay. So you always want to think about whether things are being Markovnikov, anti-Markovnikov, whether the elimination is giving you, the cis or trans, or the more substituted or less substituted, and so on like that. Okay. So let's start applying this now. All of these reactions we've learned and memorized and stuff like that, okay? Now these are, pretty boring molecules. There's nothing interesting going on, but we can't synthesize LSD or make some really cool looking things yet because, there's still some more reactions to learn, and we don't want to get too complicated, all right? So we'll just stick to the easy stuff, all right? Now I do want to give you a heads up about the format of my exam. So when you see something like this, okay, I'm normally going to say pick 3 of the 5 problems, okay? So if this clicks for you, if this clicks for you, if this clicks for you, and this clicks for you, do those 5 problems. I didn't check off 5, but you get the idea. Don't do the ones that are just too hard and you don't really, you're hitting a stumbling block. Oh, my exams and homeworks also will put a little parenthesis here, and it will say 2 steps. Okay, 2 steps. And what that means is that this synthesis can be accomplished. I see a way that I could do it in 2 steps. It might be possible that you synthesize it in 3 steps or 4 steps, or even maybe less possibly. But that's fine. There's more than one way to do these problems, and so that would also be correct. But I put the number of steps in there just so that you have an idea of, what are you dealing with? Is this like a really hard problem? Is this supposed to be 9 or 10 steps, or, what's going on, right? So let me add all these in here, and then we'll work on these problems, okay? We haven't talked about chapter 11 yet, so let's not do that one. Yeah, we skipped that problem there, and okay, this would be 3 steps. Okay. Yeah, so all of these require 2 steps except problem H, okay? I'm going to move to the next page so we have some more writing space here, I guess. So in this first problem, let me see here, take a sip of coffee. Excuse me. All right, so here are 2 carbons, right, that we need to transform to the alkyne. And this should be like a slam dunk. You know how to do the layup and get to the product really easily. So we know that we should add bromine. Okay, and that's going to put 2 halogens on those 2 spots. And then we know that we're going to have to add 2 equivalents of sodium amide to get to the alkyne. So that would be 2 steps. All right. This thing here that I'm drawing is called a synthetic intermediate. And there's no curved arrows here, okay? Don't ever worry about curved arrows here. We're doing synthesis. Now, if you wanted to write all of these out on the arrow, it would look like this. 1, you would add bromine, and then 2, you would add 2 equivalents of NaNH2. Okay, that would be another way of writing the problem. All right, so let's do B. We've got a cyclohexane ring. And so I think the emphasis of the book here is just, look at the functional groups. We're not going to count carbons because there's no change yet, okay? So somehow we've got to get the bromine from that carbon to that carbon. And now the link here is an alkene, as I mentioned before, okay? So we wanted to treat this with, like, say, Naomi. And then we want to return the bromine with hydrogen bromide, okay? So we're not drawing it here, but there is an H here, okay, on this terminal carbon, and that's Markovnikov's rule, okay? Letter C is weird at first glance because this double bond is magically changing. So is there an alcohol? Is there an alkyl halide? Is there an alkyne intermediate? What's going on here, okay? There's 2 ways to solve this. I'm not going to solve this every which way possible, but one way to do this problem is to change this to the alkyl halide. Now remember, Markovnikov's rule states that the richer get rich, and so we want to stick the bromine on the more substituted carbon. And then we want to make that double bond switch to a more substituted position. That's the Zaitsev rule, so sodium ethoxide would be good for that. Okay. For reaction D, and these also would make good flashcards too. If you've already exhausted your flashcards and you want kind of like a more complicated thing, try putting these on flashcards. D, we said we were skipping. E is a molecule that has an alcohol in it, and we are transforming it to a more substituted alcohol. Okay, and so once again we need to change this oxygen from the secondary carbon to the tertiary. Okay, so that's something to look at. That dotted yellow dot is a secondary carbon on the left and a tertiary carbon on the right. So that could help us orientate things, okay? Now we need to do an elimination here. So you could use tosylate if you wanted to. I was just thinking of using, you know, acid and some heat, and this would not rearrange or anything. It would, you know, give you the more substituted 1, 2, 3. Yeah, it might give you some of the other substituted product, but I would accept this as an answer. And so now how do we get the oxygen on the more substituted carbon? Well, you just add water and then acid again. For molecule F, this is a good problem here. F is a good problem. Let's see. So we've got an alkyl halide, and we're changing that to an alcohol. Now we just can't, you know, think, oh, this is a substitution reaction, because something else is going on here. We've got bromine here, and then we have OH there. So what do we do? We could do an elimination to get a double bond in the molecule. Okay, the way to do that is with sodium ethoxide, which would give us the Zaitsev product, and then we could add, you know, an OH back again, and we do that by adding water and acid. Okay, so you're starting to get the idea here. Now H is the most difficult problem, and why is that so difficult? It's because we have to pay very close attention to regiochemistry and rearrangements. So this carbon here is secondary, but we have to watch out for this carbon here because it has so many carbons attached to it. If we made the secondary carbocation, it would undoubtedly rearrange. So if we made a carbocation, I'll put it in brackets so you know that's like a curved air reaction intermediate, this would rearrange, okay? So we don't want to do anything with carbocations. Now, what I'm thinking in my mind is that I'm going to need a carbon-carbon double bond or an alkene between these two dotted purple positions, okay, these carbons. And that's so I can get the OH back on the other one. So how do I make an alcohol to an alkene? Normally I treat it with acid and heat, right? But we don't want to do that because that'll make a carbocation. So the alternate, very gentle way of doing this is to treat this with tosyl chloride. PYR is pyridine. Sorry about that. Pyridine. That will make your tosylate, which is a good leaving group. Okay. And then we want to make that into an alkyne, and there's really only one beta hydrogen, so we could use anything we wanted to. We could use Naomi for that. Now I want to think about how do I put a hydrogen on that carbon and an OH on this carbon, and that's anti-Markovnikov addition. We would want to use borane followed by basic hydrogen peroxide, NaOH I meant to write. Okay, so this one, I would not be able to do it any better. That's 1, 2, 3 steps. Okay, so when you're doing homework and exams, pay attention to the number of steps. Sometimes you see it, sometimes you don't, and it really sucks when you just can't see it. So that's why I give you 5 or 6 different problems, and I say write out the reactions needed to synthesize 3. Okay, choose to do 3 of the 5 following problems. Okay, so I try to help you out in that regards. Okay, now what we get into here is section 12.3, reactions that change the carbon skeleton. Okay, so obviously take a look at what functional groups are changing, but if you've got something like this, we have way more carbons in the product here. Okay, so something's going on there. We just aren't going to treat this with acid and add water. You know, we need carbons. And remember that your alkynes can be used to stitch on carbons, because this bond right here can come from alkylation. Okay, this dotted line and bold line are just my way of highlighting the bond. Okay, so this bond, I'm kind of showing scissors to imagine how I would form that. So the answer for how to synthesize this would be, you know, to take acetylene, all right, and we could add sodium amide to this. That would, you know, be step 1 there. And you would form your acetylide ion. I'll draw it with the ions drawn out there. And remember again that this guy here is a great nucleophile, and this guy here is a great electrophile. Okay, and so what you get is, well, what would we want to add? We would want to add our alkyl halide substrate, and this carbon right here that I'm highlighting in yellow is going to bond to this carbon here in an SN2 reaction. Okay, SN2, and that gives you the target molecule. Remember, we oftentimes abbreviate the target molecule TM because we don't want to draw that whole thing out again. It's just too much. Okay, this is worked example 12.2, I guess it is, and I urge you to look at that problem. The book has a different way of explaining things, and it's, you know, a page and a half of different things and considerations. Okay, so 12.7 is going to be a great problem here. So let's take a look at that. 12.7. Remember again, sometimes I feel bad about doing all of the practice problems in the book, but remember again, it says need more practice. It's like the got milk, and it says try these problems. Okay, so if you want to study more, do these problems right here to gain more practice. I'm just working through these to easily come up with some relevant examples, not anything crazy and way off in outer space, which I can easily do if I'm not guided. All right, so what do we got going on here? Well, I've got an alkyne, okay, and I'm going to need to add 1 carbon here. That's called a methyl group. And I'm going to need to add 2 carbons here. That's an ethyl group. Okay. So what I'm going to need to do is to, let's use a different sheet of paper here, and I'll show you what the answer is going to look like, okay? So again, I'm starting with, this is called acetylene. Okay, you need to memorize that. Sometimes we just type that out. So here's acetylene. I'll draw the H's in there. And if I treat this with sodium amide, remember again, I make the sodium acetylide, and I like to draw it out with the ions separated there. And then if I treat this with my first alkyl group, CH3Br, I'm going to make an alkyne that has one new carbon. Okay, so there's my methyl group. And now basically I need to rinse and repeat. Okay, so I'm going to add, we're labeling these, right? So step 3, I'm going to need to add sodium amide, all right, to this. And that's going to form the acetylide on the left-hand portion of this molecule. Okay, I'll try to keep my color codes in here. And remember again, I want to add an ethyl group. So the way to do that is to add, I'll do it in yellow again, ethyl bromide or bromoethane. Okay, and that's going to form my target molecule. Okay, so the acetylene was had dual functionality. Okay, it had an H on the left and an H on the right. And so acetylenes, or alkynes in general, are very useful for synthetic chemistry. Okay, so that's how you solve part A. Okay, 12.7a. So for molecule B, we are not starting with an alkyne. We're starting with an alkyl halide. This is an RX, right? An alkyl halide. And somehow we're snapping on this, okay? That alkyne can be as complicated in the world, but it's this bond right here that we want to make, okay? So we want to stitch this together, and I'll show you how that's going to work, okay? So here's our target molecule. Let's draw it all out. Okay, so I know they give you an alkyl halide, but before we do that, we need to take our acetylene and functionalize it, okay? Make it a suitable nucleophile. Sodium amide will once again convert this to the acetylide, okay? And then if you treat this with the provided alkyl halide, this will give you the product, okay? Now this isn't part of the answer, but you might just be wondering, well, why? How did that work? Well, remember again that alkyl halides are good leaving groups, and acetylides, because of their negative charge, are definitely good nucleophiles. And so this carbon can attack that carbon, thereby making a new carbon-carbon bond. Okay? And so that's how you do that problem. So let's look at that again. When you have an alkyl halide going to an alkyne, you need to think about what acetylide could be used. Okay? And it says identify reagents. We could use anything we want. Okay? How about this? There's definitely something going on. Count the carbons. There's a C with some hydrogens there, and it's gone. So we're missing a carbon. Now recall, I'll just do 12.7c here on the bottom here, that you can do ozonolysis on alkenes. And technically this is a one-step kind of thing, because you definitely don't want to isolate the intermediates here. But here you'll make the ketone and formaldehyde, which goes in the trash can. Okay, so we don't write, you know, this we don't draw. All right, so in this problem, they didn't draw it, okay? They're not trying to trick you. It's just we're not in the business of making formaldehyde, okay? We're in the business of making 4-heptanone. 2, 3, 4, 5, 6, 7, 4-heptanone. All right, so it's getting more complicated, okay? Problem 12.8. And again, I just want to refresh your memory. Try these problems if you want to try more synthesis problems, okay? All right, so what do we do here? So, count the carbons, okay? So 1, 2, 3, 4. And then we have 1, 2, 3, 4, 5, 6. Now, whenever your carbon count increases by +2, it's a good guess to imagine that those 2 carbons are coming from acetylene, okay? So let's do problem 12.8 on the next page. That's problem A. So again, we want to transform the 4 carbon containing starting material to an alkene that contains a total of 6 carbons. So what I'm going to do is take acetylene and I'm going to attach these molecules, these 2 carbons, to this end of the molecule by treating it with sodium amide. Okay, and again, that makes the acetylide. Okay, and now I want to add the molecule provided to us, 1-bromobutane, and that's going to get a molecule that has the correct number of carbons. Okay, so this has 6 carbons now. Okay, this had 4, now we have 6. Now we just simply need to think about how do we change an alkyne to an alkene, and we can do any of the available methods. We could use sodium and liquid ammonia, and that will change the alkyne to an alkene, and there's no change in the carbon count. Okay. For problem 12b, so oftentimes the functional group is a handle. It's a toe hold kind of thing for climbing a mountain, and it's useful for manipulating things. So, but first let's count the carbons here, okay? You can see this isopropyl kind of feature on this side of the molecule is the same, so you want to line things up. And here we have 2 additional carbons, okay? 2 additional carbons. And here we just have one carbon. So we're missing a carbon. The way to miss a carbon or eliminate it from your molecule is with ozonolysis. So you want to think about doing an ozonolysis here. So let's try to do that. Let's take our starting molecule and let's treat it with a base to do elimination. Now think carefully about where you want this double bond to be. I want it to be around this dotted portion here, which means I cannot do sodium ethoxide. If I did Naomi or sodium ethoxide, that would give me the Zaitsev product, and that's not useful. Okay, the double bond is going the wrong way. So we want to use potassium tert butoxide. That's how we write that. And this is going to give us the Hoffman product, where the double bond is between these two carbons here. And now we can take this and destroy it by treating it with ozone and zinc and acid. And that will give us an aldehyde. And, you know, formaldehyde is where that other carbon comes from, but goes, but we don't really draw that. Now keep in mind we generally draw that aldehydic hydrogen, right? We draw that H. So yeah, that's how you do this problem. It's 2 simple steps, but there's a lot of detail and a lot of analysis that goes into figuring that out. By memorizing your reactions, this problem is a lot easier to solve than if you're totally struggling with your reactions. Problem 12C. Three carbons. Five carbons. So once again, we want to add 2 carbons to this. Let's think about adding the 2 carbons from acetylene. So for my synthesis, let's start with acetylene. Remember again, if you're provided with an alkyl halide, you actually want to start with something else called acetylene. Treat this with sodium amide. And if you're noticing some certain amount of repetition, that's good. You're seeing the patterns. Now, how are we gonna stick these 2 carbons onto something? Now we use this. Okay, now we use this. So I'll draw it in yellow. And what we make is a molecule that looks like that. So here's my 3 carbons from my starting point. Here's my 2 carbons from my acetylene. And so now I've got the carbons. So now how am I going to make that alkyne change into that? Well, that's easy. We just add 2 equivalents of HBr. Okay? And that's a memorization reaction. Okay? So, you know, 2 or 3 steps depending on how you count those steps. Okay? Now 12.4 kind of gives you a very good. 12.4 is probably the most important section of the whole book. It's basically about synthetic strategy, okay? Number 1 says, is there a change in the carbon count? So first you count carbons, okay? And if there's a change, think about using acetylene at this point, or using an alkyne at this point, okay? Or ozonolysis to remove a carbon, something like that. After you finish counting the carbons, then you want to think about the location and the identity of the functional group, okay? Does it change from carbon 2 to carbon 3? Does it change from an OH to a Br? You know, and those sorts of things, okay? So it's not very helpful, I know, but definitely think about these 2 things, okay, in your analysis, all right? Once you have figured things out, you want to think about if, for example, your carbon count increases by 2 carbons, you want to use acetylene, okay? If it decreases by 1 carbon, you want to use ozonolysis. If it's an alkene, it's hard to talk and write at the same time. If it's an alkene, you want to use ozone followed by zinc and acid. If it's an alkyne, you want to use ozone followed by water. Okay, so be watchful for the different types of things there, okay? If you're starting with an alkyne and it increases by 3 or 4 or 5 carbons, you want to think about alkylating your alkyne. Okay, so for example, if you had a molecule, like that, and you were changing it to of course, you're adding 2 carbons in place of that hydrogen, you wouldn't want to use acetylene. You'd want to use an alkyl halide. So you'd want to think about using an alkylation and think about what alkyl halide you'd want to use. Okay? And then you want to think about what specific reagents would be able to do that. Okay? So let's do problem 1210, and this is basically, what we're looking at. Okay? Now, you'd be quite amazed. Let me show you in the book. So here's problem 1210. All right, we'll do that. And then you look on the bottom of the book, and that's not a typo. It says try problems 19, 20, 21, 22, 23, 24, 25, 26. Okay, all of those problems are just like the problem I'm going to do now. Okay, and really my strategy is that there's no better way to learn this than just doing practice. Okay. So let me think through and try to verbalize the strategies that we've discussed so far and see what we can do. All right, so this is problem 1210. Okay. So for letter A, we want to count the carbons. So we've got 1, 2, 3, 4, 5. And you'll notice that they line up with that. Okay, so we're adding an additional 1, 2, 3. Okay. How do we add 3 carbons? We added it with a 3 carbon fragment. So, first we have to make the acetylide. Okay. And then we need to add 3 carbons. So those are 3 carbons there. Okay. Now that doesn't make the double bond, right? We now need to think about how do we go from a triple bond to a cis double bond. And the way we do that is with Lindlar's catalyst. Okay. So the most important part with those dots, analyzing the number of carbons and seeing where those new carbons came in. They came in adjacent to my functional group, so that means that I had to do an alkylation. Okay. Problem B, it looks weird because my additional carbons are way over here on the left. I can't do that. There's no way to add new carbons to just an alkyl, an alkane functional group. So I need to add the new carbons on the end here. Okay. This particular problem, I'm not going to do this one because we have to do one of those reactions that we haven't talked about. We skipped it. Okay, so let's skip this problem here. Now for problem C, whoops, we're missing a carbon. Now this is a carboxylic acid functional group. And on my flashcard, I happen to have this reaction here. Okay. So I know that's one of the ways to make one of my carbons missing. Ozonolysis. Okay, you just need to memorize that. There's only one way to make one carbon disappear, and that's through ozonolysis. So far we've learned in the class. So now I need to think about, well, how do I make an alkyne? The way I make an alkyne from a vicinal dibromide is with 2 equivalents of sodium amide. And then I want to do the ozonolysis. The ozonolysis is technically 2 separate steps, but that's how you would change that to the carboxylic acid. Okay. Um, let's kind of skip this one maybe. All right. This one is quite complicated. It's a lot of, I don't see a faster way of doing this, but let's do it on the adjacent page. So, we're adding carbons in a weird spot. Okay. I'm adding 2 carbons. So I know I need acetylene. Acetylene looks like this. And this part of the molecule, I need to make that be an alkyl halide. And I don't quite see an easy way to do that from the given molecule. So that's why I say it's kind of a pedestrian synthesis. I'll have to do this, then this, then this, then this, and then, to eventually get that, which is probably like, $20 a kilogram or something that you can just buy. But let's do problem E, okay? Problem E. And oftentimes synthesis becomes this procedure where you're like, okay, let me take it back one step. And remember how you take it back one step. We use the retrosynthesis arrows. We think backwards and we're like, well, I know the very last step in the synthesis is going to be this, plus, my acetylide business, right? But then how do I make this? Well, I'm not sure, but I have this starting material and I need to work all the way to the end there. So how am I going to do that? Well, I need to get the double bond to go from these 2 carbons to these 2 carbons here. Okay. So how do I do that? Well, I'm thinking in my mind that I need a different functional group like HBr or something. So, or an alcohol or something. So I'm going to treat this with hydroboration. Now I'm choosing hydroboration because I know this goes by anti-Markovnikov. And therefore my alcohol will move in the direction I need it to be. Okay, it's going to be over here, which is on a purple carbon, right? It's one of these purple dotted carbons. Now I need there to be a double bond between these 2 carbons. And if I treat this with acid, my double bond's going to go back over here. That's not where I want it. So I'm thinking that I need to treat this with tosyl chloride in pyridine. Okay. And then once I have my tosylate, then I can treat this with a bulky base. Remember that potassium tert butoxide is very special, and it gives you the Hofmann product, where the double bond is less substituted. It's unstable, less stable, right? So it's over here. Now I have my double bond in the right spot, and then I have to go and complete the synthesis. And I just realized it's hard for me to think this through all in my mind. We have to choose a a reaction that we skipped. So I don't know how you would synthesize this. Okay, we didn't even talk about this one, but this would get me my anti-Markovnikov halide, and then I could treat that with sodium acetylide, which would give me the target molecule. I don't like this synthesis too well because I'm doing 2, 3, 4, 5, like bazillion steps. All right, so I don't like these kind of problems. I like 2 to 3 steps synthesis. That's what I assign anyway. Okay, so I should have skipped problem E. Problem F is doable. If we look at this molecule here, we can see that there's 2 carbons hanging off. There's only 1, so we need to do ozonolysis. Ozonolysis is performed on alkenes or alkynes. So I need to think about how do I make an alkene between these two carbons. I want a carbon-carbon double bond between those two carbons. So you might be thinking, well, just treat this with acid. You know, we did this reaction in the lab, right? But if you treat this with acid and heat, this is going to give you the more substituted alkene. So that's the wrong way. How do we get the alkene to go on the right? Well, this is where we would choose to use the tosylation procedure. So if I treat this with toluene sulfonyl chloride, pyridine, this would make my tosylate. Okay, and then I could treat this with potassium tert-butoxide to give me the Hofmann product, or the less substituted alkene, and then I could blast on it with ozone and my zinc and acid, and that's going to cleave that carbon away, and that's where the missing carbon goes. It goes to, formaldehyde, right? So those are just some questions, and I very much urge you to try problems 1219 to 1226. If we look at 1219 through 1226 in the book, I did make a modification here that I would like to share with you. Let me just open the camera and we'll look at some things. Okay, so do this problem 1217. That's a review. Do this problem 1218. That's a review. For 1226, so here's a bunch of problems that you should work on. All right, so there's various things to think about. For 1226, I've changed the given double bond to the halogen there. So start from the halogen and see if you could make these other ones. I believe all of these can be done in, 2 steps, okay? 2 steps. So try to do the ones that are 2 steps or 1 step from the book. And that's pretty much it. There's just a bunch of challenge problems, but I'm not really worried about that. We're not like, all chemistry majors or something. But do maybe this one here, and definitely these, what I call spider diagrams, okay? Put an alkene of your choice in there, but this alkene's already been chosen for you, okay? So that's it for today's lecture, and we'll do a little bit more on this chapter, I believe, and then we're done, okay? So I'll talk to you later.